What's up, Algebros and Broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, welcome. Today we're going to take a look at section 1.2. We're going to talk about row reduction and echelon forms. So this is where we're starting to talk about what it is we're looking for out of our row reduction. We have a rectangular matrix is an echelon form, or we could say row echelon form, if it has the following three properties. First, all non-zero rows have to be above any row of all zeros. Second, each leading entry of a row is in a column to the right of the leading entry of the row above it. Third, all entries in a column below a leading entry are zeros. Now we continue on with this list and say, if a matrix is an echelon form, it satisfies the following additional conditions, then we'd say it's in reduced echelon form or reduced row echelon form. And I usually like to call it a fully reduced row echelon form, just to really get that idea across. So we need these next two conditions to have that reduced echelon form, which is fully reduced. We need that the leading entry in each non-zero row is 1, and each leading one is the only non-zero entry in its column. And we got Gabby to help us out. She says, let's do linear algebra together. So we're all hanging out together. Got the cats helping out, so that's good. We need the leading entry in each non-zero row is a 1, and that each leading one is the only non-zero entry in its column. So that's what we're talking about here. So let me just go back through and recap on this. We have an echelon form, or row echelon form, but not fully reduced, if it has the following three properties. If you have a row of all zeros, they got to be at the bottom. A row of all zeros, bring it to the bottom. Second, we need each leading entry of a row in a column should be to the right of the leading entry of the row above it. This means we want to have this nice diagonal fall. I don't know what your orientation should look like, but we want these to sort of fall in a nice diagonal pattern from, upper left to bottom right. It doesn't have to be perfectly like that, but it wants to follow that trend. And then we want to make sure that for those leading entries, everything underneath them are zeros. And then we have that echelon form. If I'm looking for that fully reduced row echelon form, I need the leading entries, I need them to all be 1s, and I need to make sure that they're the only entry in the column that isn't a 0. Okay, so let's go ahead and try to see if we can apply this. All right, so here, and again, we're talking about leading entries, meaning the leading entry of a row refers to the leftmost non-zero entry in a non-zero row. And I'll sort of talk a bit about how I like to determine that. So we want to figure out which of these matrices are in reduced echelon form and which ones are only in echelon form without that full reduction. So what I want to do is I want to go through and I want to sort of go to each row and I want to move in from the left until I hit the first entry. So right with row 1, I hit that entry right away and I see everything above and below it is a 0. So it's really good. It's a leading one. Everything above and below is a 0. If I go into the second row, I pass through any 0. And then I hit the leading entry, which is this 1. I pass through any 0, gives me this 1. My leading entry is a 1, which is good. Everything above and below it is a 0, so that looks really good. And in this third row, I'm looking for my leading entry, but I pass through a 0, I pass through another 0, and then again and again. So there's actually no leading entry. And it is a row of all zeros. It is at the bottom. So this is actually an example of something that is in fully reduced row echelon form. So this is fully reduced row echelon form. This one is perfect, so it gets the smiley face. Let's move on to this next example. Again, I want to talk about the leading entries, so we pass through any zeros and we move in from the left. So here from the left, we hit that leading entry. It's a 1, which is good, and it's the only non-zero entry. Everything above and below it is a 0. There's nothing above it, but everything above and below it is a 0. Move on to the next row. I pass through the 0, and then I hit the leading entry. My leading entry is a 2 in this case. But we say, okay, so that's worth noting. It's not a leading one, but let's check the other. got a 0 above and below it, so it looks really nice. And then I'm going to go to the third row, pass through the 0, pass through the 0, and then I hit my leading entry, which is a 1, which is good, and everything above and below it are zeros. So everything's looking really nice with that. Now in this case, I have something that is an echelon form, but we'd say, but not fully reduced. So this gets sort of the, am I happy? I'm not really super happy face, but still good, right? Echelon form, not fully reduced. In fact, the issue with it is that the leading entry isn't a 1. I have a leading 2 in this case. Okay. Now let's look at this next example. If I'm looking in row 1 for that leading entry, I pass through the 0 again, again, and again, and there's no leading entry, and in fact this first row is a row of all zeros. Right away it's a big issue. If I have a row of all zeros that needs to be brought to the bottom, I can do that with the row interchange. So this in fact is neither. Right, this is not echelon form. It's not fully reduced echelon form then, since it needs to first at least be echelon. It doesn't have those 3 criteria met, and so it's not going to have all 5 definitely. So this is actually no good. We could fix it, right? If we did row operations, we could improve on this definitely. But as the question states, I'm looking at this matrix as I'm given it. Man, it doesn't look like it's not going to be echelon or reduced echelon. Let's take a look at this last example. Remember, we're moving in from the left. I pass through a 0 and I hit my leading entry. It's a 1, which is good, and it's the only non-zero entry. So far, so good. Now I go to the second row, I move in from the left, I hit my leading entry, it's a 1, and I notice I have zeros underneath it, which is good, but I don't have the zeros above it. So right away I have an issue that we want to sort of take note on, but we sort of make a mental note of it, and then we go on, finish searching. Now I go to my third row, I pass through the zeros again and again and again and again, and I hit my leading entry, which is a 1, which is good. 0 beneath it, but I don't have zeros above it, so that's no good. And then here, my last row is a row of all zeros, and it is at the bottom, which is nice. So this is actually a very nice looking matrix. This one is echelon form. Echelon form, but not fully reduced. And the issue is that even though I have the leading ones, they're not the only non-zero entries in their columns, right? I have some other values above them. So this gets the, I'm not quite sure if I'm happy face, right? So this one actually has the issue with statement number 5. So just sort of recap, I need 0 rows all at the bottom. I need this nice diagonal sort of motion to the leading entries. I'll go over that in just a second. I need the entries below a leading entry have to be zeros column-wise. And to get that fully reduced row echelon form, I need the leading entries to be 1s, and I need that the leading one is the only non-zero entry in its column, so zeros above and beneath it. But if I notice, these all sort of have this really nice sort of diagonal flow to them from upper left to bottom right. I'm sort of not looking at zeros, but I'm looking at leading entries. So that happens, and there's no leading entry here, so it kind of stops, and this one's got that nice diagonal flow to it. We said the issue was that I don't have that leading entry as a 1. I could scale it, of course. And this one has a problem, right? The row of all zeros at the top is not what we want. We're going to want to do a row interchange to fix that. And this last one has that really nice diagonal sort of flow to it. You know, don't be sort of thrown off by the fact that everyone's got a 0 at first, you know, but I still have that nice diagonal flow for the leading entries, and then here it kind of like jumps over, but it still follows that motion, which is really good, very nice. But not nice enough, right? Because we need the zeros above. And we could do that with row reduction. Let's take a look at some definitions. You have a pivot position in a matrix A is a location in that matrix that corresponds to a leading 1 in the reduced echelon form of that matrix. A pivot column is a column of matrix A that contains a pivot position for some matrix A in reduced echelon form. So what we're going to do is we're going to take this matrix, just a normal regular matrix, think of it like a coefficient matrix. We're going to row reduce so that we can get it into a reduced echelon form. So we're going to do the full reduction, and then we're going to circle the pivot positions in the final and original matrices and list any and all pivot columns. Now we might be able to answer the questions, part of them, without going to a fully reduced row echelon form, but we're going to go for the full reduction here. For this good practice, we're going to want to get into that mindset. To start off, I can actually use this leading 1 in the upper left corner to get zeros underneath it, and that's what I want to do. So I'm just going to start by rewriting row 1. And then I'm going to go in row 2, and I'm going to replace it with row 2 minus 2 times row 1. And I'm also going to work in row 3. I'm going to replace row 3 with row 3 minus 4 times row 1. And I don't want to try to do too much at once, but I should be successful. So let me go to row 2, replacing with row 2 minus 2, row 1. So I get 2 minus 2 times 1 gives me 0, which is good. 4 minus 2 times 2 gives me 4 minus 4 gives me 0, so that's nice. 5 minus 2 times 4, that's 5 minus 8, gives me negative 3. And then 4 minus 2 times 5, that's 4 minus 10, gives me negative 6. But I'm also doing a row replacement in row 3, replacing with row 3 minus 4 times row 1. So that's 4 minus 4 times 1 gives me 0. 5 minus 4 times 2, that's 5 minus 8, gives me negative 3. 4 minus 4 times 4, that's 4 minus 16, gives me negative 12. And then 2 minus 4 times 5, that's 2 minus 20, gives me negative 18. Now what I'm going to do next from here is I'm going to do some scaling. So I'm going to scale row 2 by a negative 1/3. So row 2 by negative 1/3. And I'm going to scale row 3 also by a negative 1/3. I'm going to rewrite row 1. It looks good so far. We'll critique it later. And if I divide everything in row 2 by a negative 3, I get 0, 0, positive 1, positive 2. If I go to row 3 and divide everything by negative 3, I'm going to get 0, 1, positive 4, and then positive 6. So just dividing everything by 3 and flipping the sign. This looks good so far, but I actually want this diagonalization to fall sort of, well, I shouldn't say diagonalization, that's going to be another term for us later. I want the diagonal entries, the leading entries, to follow this nice kind of diagonal pattern, but it's a little kind of crisscrossed here. I should really be swapping rows 2 and 3. So I'm going to put row 3 in row 2's position, row 2 in row 3's position. I'm going to leave row 1 where it is. So I'm just rewriting that. But then my new row 2 is going to be this 0, 1, 4, 6. And my new row 3 is going to be the 0, 0, 1, 2. Now from here I want to keep working with my reduction, though I can probably start to get a sense as to where my pivot positions are going to be. Let me start in row 3. So I'm passing through my zeros. I hit that leading entry as a leading 1. I want to get the zeros above it. Right? There's nothing beneath it, but I want the zeros above it. So I can actually work in rows 1 and row 2. I can replace row 1 with row 1 minus 4 row 3. And I can replace row 2 with row 2 minus 4 row 3 as well. Similar operation there. Let me rewrite row 3 and just get that out of the way. Here in row 1, I get 1 minus 4 times 0 gives me 1. 2 minus 4 times 0 gives me 2. 4 minus 4 times 1 gives me 0. And 5 minus 4 times 2, that's 5 minus 8, gives me negative 3. Replacing in row 2 with row 2 minus 4 row 3, I get 0 minus 4 times 0 gives me 0. 1 minus 4 times 0 gives me 1. 4 minus 4 times 1 gives me that 0 that I had wanted. And then 6 minus 4 times 2, that's 6 minus 8, gives me negative 2. Now I'm almost done. So here, if I go in, checking from the bottom, moving in from the rows, I get my leading entry is a 1. Everything else is a 0 in that column. If I go to row 1, I actually already have that too. Right? So here, that leading entry is a 1, and everything else in the column is a 0. But row 2 isn't quite, that second column. If I move in from row 2 and hit that leading entry, the 0 underneath it, but I'm missing the 0 above it. So the issue isn't really with row 2, but I can diagnose it by moving in through row 2 and hitting that leading entry. It's really column 2 that I'm sort of critiquing. And I say it's that, in particular, it's that entry, that 2 above it, that I gotta fix. Gotta fix it up. So I'm gonna work in row 1. I'm gonna replace row 1 with row 1 minus twice row 2. Let's see what that's gonna look like. So let me rewrite rows 2 and 3, just because they're not gonna change. But I am gonna replace row 1. So I get 1 minus 2 times 0 keeps my 1. 2 minus 2 times 1 gives me that 0 that I had wanted. 0 minus 2 times 0 gives me 0. And negative 3 minus 2 times negative 2, that's negative 3 plus 4, gives me positive 1. Now everything is fully reduced now, so we can check again. So I'm moving from the left. Leading entry is a 1. Everything else is a 0 in its column. Row 2. Pass through the 0. My leading entry is a 1. Everything else in the column is a 0. Row 3. Pass through the 0. Pass through the 0. My leading entry is a 1. Everything else in the column is a 0. No other rows to check. This is fully reduced. So here I have the fully reduced row echelon form of this matrix. So let me go ahead and just write that out. So we had first row 1, 0, 0, 1. This is not an augmented matrix. 0, 1, 0, minus 2. 0, 0, 1, 2. So we're not actually solving a system. That's not really what we're talking about at the moment. We're just sort of talking about pivot positions. These leading entries are my pivot positions. So I have a pivot position, the first entry of row 1. I have another pivot position, the second entry of row 2. And I have another pivot position, the third entry of row 3. Now the instructions asked me to also circle those same pivot positions in the original matrix. So I just want to remember the locations and circle them in here. So in the original matrix, it was first in row 1, second in row 2, third in row 3. The real reason why this would matter isn't so much that I really care about these kind of pivot entries. What I really care about are the pivot columns, the columns that contain a pivot position. So if I'm looking at the columns, I see column 1 has a pivot position in it, column 2 has a pivot position in it, and column 3 has a pivot position in it. Column 4 does not have any of these pivot entries, no pivot position in column 4. So we would mention that. We would say the pivot columns are 1, 2, and 3. And certainly circling the pivot positions is good, but we're going to want, especially later on for our course, is to really focus on these pivot columns. For now, we'll leave a bit of an air of mystery about that, but the pivot columns are going to be very important to us. So we have pivot columns 1, 2, and 3. Let's continue. Let's talk a bit more about what we sort of can figure out from these pivot columns and reducing matrices. I want to find the general solution of the following system with the given augmented matrix. So right away I can actually start reducing. And I can work in row 2. I can replace row 2 with row 2 plus twice row 1. So I can rewrite row 1 to start. 1, negative 2, negative 1, augmented with 4. But working in row 2, I get negative 2 plus 2 times 1. Negative 2 plus 2 gives me 0, which is why I picked this operation. I want to get that 0 underneath my leading 1. And then I'm going to have 4 plus 2 times negative 2, or that's 4 plus negative 4 gives me 0. And negative 5 plus 2 times negative 1, that's negative 5 plus negative 2 gives me negative 7. And then in the augmented entry, I'm still doing this operation. 6 plus 2 times 4 is going to give me 6 plus 8 is going to give me 14. Now I can actually reduce row 2, I can scale it. So I want to scale row 2 by a negative 1/7. So I have my first row 1, negative 2, negative 1, augmented with 4. The second row is going to give me 0, 0, 1, augmented with negative 2. So dividing by 7 and flipping the sign. And now I can reduce a bit further. So this first leading 1 looks really good in my coefficient matrix. But my other leading 1 in row 2, I need that 0 above it. So we'd say, well, let's keep reducing. I can replace row 1 with row 1 plus row 2. So 1 plus 0 is 1. Negative 2 plus 0 is negative 2. But I picked this operation, so I could do negative 1 plus 1 gives me 0. And then augmented with 4 plus negative 2 gives me 2. And I can rewrite row 2. So it's 0, 0, 1, augmented with minus 2. Now at this point, everything is fully reduced, so all that's left is to start writing out the solution. But something that you're going to notice about this that I want to sort of point out preemptively are where we have our pivot columns. So my leading entries are my pivot entries. So I have a pivot column in column 1, and then column 2 isn't a pivot column, right? This entry, this minus 2, isn't the leading entry. The 1 was the leading entry. So I'm sort of working row-wise. If I go to the second row, here's my leading entry, and it lives in its pivot column. My pivot columns are 1 and 3 in this case. I'm really only looking at the coefficient matrix. Now what that's going to mean, and we'll talk about this a lot in the course, these are where my basic variables live. And if I have something that is not a pivot column, that's where my free variable is going to live. So the second column is not a pivot column. That's where my free variable lives. And try to think back to what we said in the very first lecture. These columns represent where the variables live. So this would be where x sub 1 lives. This would be x sub 2. This third column would be for x sub 3. And these are just the coefficients on that variable. So we're really saying that the non-pivot column is where the free variable lives. In this case, x2 is a free variable. So I'm going to jot that down as well. x2 is a free variable. And that's because it is not in a pivot column. Pivot columns refer to basic variables. If it's not in a pivot column, it refers to a free variable. And let's see how that's going to come into play when I write out my solution. So let me just write these out as equations, row by row. So this first row is telling me 1x1 minus 2x2 equals 2. The second row, and I can sort of skip over the zeros, 0x1, 0x2, says 1x3 equals negative 2. The goal here, or my motivation, is to solve any basic variable in terms of its free variable. So I want to solve for x2. And I can do that in this first equation. I could say x sub 1 is equal to 2x sub 2 plus 2. I'm just adding that term over. And then x sub 3 is equal to negative 2. If I want to mention what's happening with x2, I should do that in between x1 and then x2 and then x3. I would say x2 is free, or is a free variable. And this gives me my complete description of my solution. So in fact, we get a lot of different possible solutions, infinitely many. All you have to do is pick x2, and then it will fix what that solution looks like. x3 is always negative 2, but x1 depends on this free variable. So for example, I can give infinitely many solutions, but I could give you a couple of examples. You could come up with many more. x2 is where I have my freedom. So if I pick x2 to be 0, then x1 would be 2 times 0 plus 2, which is 2, and x3 is always negative 2 no matter what. So this is a solution, or I could do this differently. I could say, well, what if I let x2 be 1? Well, now x1 relies on this, so I get 2 times 1 plus 2, which is 2 plus 2, which is 4, and x3 is always negative 2. So this is another possibility. And I could keep going on and on with this, so I'll say or dot dot dot. So I have infinitely many solutions here. You have that choice of freedom on x2. We have that free variable. Let's find the general solution for another matrix. Now let me go ahead and start by sort of critiquing how this looks. If I go to this first row, there's my leading entry, it's a 1. Everything underneath it is a 0, it looks good. Second row, there's my leading entry, it's a 1. Everything above and below it is a 0 in its column, it looks good. If I go to row 3, pass through the zeros, there I have my leading entry is a 1. However, I have an entry above it that's not a 0. Otherwise it looks good, the negative 8's gotta go. And this last row is a row of all zeros. And it's important that the augmented entry is a 0 as well. This is saying 0x1 plus 0x2 plus 0x3 plus 0x4 plus 0x5 equals 0. If this was like a 2 or a negative 7 or something, it would give me a false statement, and I'd be able to see right away that I have an inconsistent system. But so this is good then. The only issue that I have is with this negative 8, and I want to get rid of it, so I can do a row operation in row 1. I can replace row 1 with row 1 plus 8 times row 3. So doing that, I get 1 plus 8 times 0 is 1. 0 plus 8 times 0 keeps my 0. Negative 5 plus 8 times 0 is negative 5. 0 plus 8 times 0 is 0. Negative 8 plus 8 times 1, that's negative 8 plus 8, gives me that 0 that I wanted. And then in the augmented entry, 3 plus 8 times 0 gives me my 3. So a lot of what I had was preserved. Since I was doing a lot of operations on 0, linear operations, But I was able to get rid of that negative 8 with a 0, and now I just want to rewrite the rest. So just rewriting. Now I want to go through and I want to try to figure out where my pivot columns are, all of that stuff. If it has a leading entry in it, that's a pivot entry. So here's my pivot column. This is a pivot column. If I go in through row 3, here's a pivot column. But I have 2 columns then that are not pivot columns. So it should be the 3rd and the 4th columns, and this is where I have free variables. Which means that, so x1, x2, it would be x3 and x4, not x5, not x1, not x2, but x3 and x4 are my free variables. We would say that x1, x2, and x5 are the basic variables. Now I want to write out my solution. So I just sort of go row-wise and think about what the equations are saying. This is saying 1x1, 0x2, minus 5x3, and 0x4, 0x5 is equal to 3. So that's really all I get from there. The second row is saying, okay, 0x1, so skip it. I have 1x2 plus 4x3 minus x4 plus 0x5 equals 6. And then this next row, 0x1, 0x2, 0x3, 0x4, 1x5 equals 0. And then the last row doesn't tell me anything. It says 0x1, 0x2, plus 0x3, plus 0x4, plus 0x5 equals 0, which is essentially just saying 0 equals 0. Yeah, thank you. Good to know. Already probably knew that, but good to sort of, think about it. What I want to do is I want to solve for the basic variables in terms of the free variable. So I want to solve these for x3 and x4. So I can do that in the first equation. I could say x1 is equal to, I want to add that over, 5x3 plus 3. x2 is equal to, so I have to subtract that over, we'll say negative 4x3 plus x4 plus 6. Now x3 and x4 are the free variables, so I'll just give them a mention here. x3 is free, x4 is free, and then x5 is actually 0. And this is how my solution looks. That's a description of my solution there. So I have 2 free variables here. So I get to choose what x3 and x4 would be. As soon as I make a choice about that, it fixes x1 and x2, and x5 is always going to be 0 for that entry. So I could have infinitely many solutions for this. You could get a bunch of them. Let's determine the value of h so that the matrix that we have gives us a consistent linear system. We have an augmented matrix. I want this to be consistent. I want there to be a solution. So let's see what we can do then in that case. What I could do to start here, and there's a lot of ways you could approach this, is I would try to make the rows look as similar as possible. So I would go and I would multiply this first row by either like a 2 or a negative 2. So let me do a negative 2 times row 1. And the reason is I want to try to match entries and make them look similar. So if I do that, I'm going to get 1 times negative 2 is negative 2, negative 3 times negative 2 is positive 6, and then augmented with negative 2. Then here I'm just going to rewrite h6 augmented with minus 2. Now I want to go through and pretend like I'm row reducing as I would normally. So I would do some work in row 2, replacing row 2 with row 2 minus row 1. So I'm going to rewrite row 1. In row 2's position, I get h minus negative 2. That's really h plus 2. I don't really know how that looks, so I'm going to write it as the single entry. 6 minus 6 gives me 0. And negative 2 minus negative 2 is negative 2 plus 2 gives me 0. Now I'm not even really looking at or focusing on this first row. I am looking a lot at the second row, and I want to make some comment about this. What is the second row saying? It's saying h plus 2, whatever that is a number, times x1 plus 0 times x2 equals 0. So I can write that out. And we can actually clean this up quite a bit. So I'd say, well, this is really just saying h plus 2 times x1 equals 0. You'd say, well, what comment would we make here about h? What could h be? What could h not be? Well, if I think about this, there really isn't any issue with h. H could actually be anything. Let me sort of illustrate why. H can be anything. What if h was negative 2? So we'll say if h is negative 2, and this is going to give me 0, right? Negative 2 plus 2. So I get 0x1 equals 0, which tells me 0 equals 0, which is a true statement. Right? And that would actually give me free variables to the system, which is fine, right? That's not a bad thing necessarily. What if h doesn't equal negative 2? So I go, what if it's something else? So if h does not equal negative 2, then whatever I have here is going to be some non-zero value, something positive, something negative, some constant. I don't really know what that is, but let me just call it, k, for example. I get k times x2 equals 0. K is not equal to 0. So here I'm letting k be equal to h plus 2. Since h is not negative 2, then k is not 0. And then I would just divide and solve. I would say, well, okay, so this means that if I scale this, then x2 is equal to 0, which is part of my solution then. So this gives me part of my solution. It doesn't give me a free variable, but it gives me a piece to my solution. And then I'd go back and I'd solve for x1. So in fact, h can be anything in this case. I think it's always easiest to think about what the equation looks like and to sort of explore it from there. In this case, if h is negative 2, I get a 0. It's still okay, though. It doesn't give me a false statement. 0 equals 0. Is it informative? Not really. But is it harmful? No, it's fine. If it's something else, then I would still be able to solve for this value. I'm sorry, this was x1. So I have a typo here. x1. If you're screaming at your computer screen, wondering what I did, you're right. I did it. I was wrong. This was x1. My typo. This is how I fix it. So this would just give us that x1 then is equal to 0 solving. Let's take a look at one last sort of problem. We'll talk a bit about sort of existence and uniqueness. We say a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if an echelon form of the augmented matrix has no row of the form 0, 0, 0, so on and so forth. I got all the zeros, and then augmented with b, where b is not 0. So this would be a problem. This would mean, like, if I had a row in my matrix that was 0, 0, 0, 0, and then augmented with 3. We'd say, well, hold on a second. So 0 plus 0x1 plus 0x2 plus 0x3 plus 0x4 equals 3. That's not true, right? I can't have 0 equals 3. This is inconsistent. So we'd say, okay, that's a problem. If this happens to be a 0, if b is 0, then it's fine. It just says 0 equals 0. So we're really saying with b non-zero, if a linear system is consistent, then the solution set either has a unique solution when there is no free variable, or infinitely many solutions when we have at least one free variable, like we've been talking about today. Now I want to go through the system that I have. I want to choose values for h and k, where those are just numbers, so that the system has no solution, a unique solution, or many solutions. And here I have this system, x1 minus 3x2 equals 1, 2x1 plus hx2 equals k. And the very first thing I want to do is make my augmented matrix. So that'd be 1 minus 3 augmented with 1. Second row would be 2h augmented with k. And I want to go through and work with this. So what I'm going to do to try to help out is I'm actually going to scale row 1 up. I'm going to do 2 times row 1. And that's going to give me 2, negative 6 augmented with 2. And then I have row 2 as 2h augmented with k. Now I can do some row reduction here. Looking at it, you might be able to answer some of the questions already. I'm going to replace row 2 with row 2 minus row 1. So I'm going to rewrite row 1. Here I get 2 minus 2 gives me 0. H minus negative 6, that's h plus 6. And then augmented with k minus 2, and I don't know what that looks like. But if I focus on what this second row is telling me as an equation, it's saying, okay, 0x1, so I can kind of skip over that. And then it's saying h plus 6 times x2 equals k minus 2. Now, if I want to break these down into the different possibilities, let's start by saying, when is there no solution? No solution means I get something like 0 equals not 0. That would be my telltale that I have an inconsistent system. So in order to have no solution, I would say, well, what if h is negative 6? But then what if k does not equal 2? And in that case, I would have h is negative 6, so I get 0x2 equals non-zero. So that would be my no solution. Get that inconsistent system. What about, and maybe we'll talk about next, infinitely many solutions. Well, in that case, this should really just be a row of all zeros, meaning I would get a free variable. So then I would want, 0x1 plus 0x2 equals 0 to give me that infinitely many solutions. It would give me that free variable. So in that case, I would say, well, now I want h to be equal to negative 6. But I would want k to be equal to 2. So if h was negative 6 and k was 2, I would get 0 equals 0, which is, it's true, but it's giving me that free variable. If I want to talk about one solution, a unique solution, we have a unique solution when simply h doesn't equal negative 6. Because if h doesn't equal negative 6, think about what's going to happen here. I'm going to get some value in front of x sub 2, and then I would solve for x sub 2. It would give me some leading entry here. I'd scale it to a leading 1, and then I could solve for what x sub 2 is supposed to be. Right, this would give me some non-zero value, and then I'd be able to solve for x2. So you'd say, okay, for a unique solution, h just would not want to be negative 6. That keeps my leading entry as some non-zero value. I can then work ahead and solve. So these are the three possibilities. We'd say no solution when h is negative 6, but k isn't 2. That gives me inconsistent. It gives me a false statement. Infinitely many solutions when I have this row of all zeros, because it's going to give me a free variable then. So h would be negative 6 and k would be 2. Gives me all the zeros. And a unique solution when I just have this leading entry as a non-zero entry, meaning that h can't be negative 6. Anything else for h will work, and no restriction on k. So that's what we're looking with. That's it. I have this extra sheet here for you to jot your notes down on. I'm going to make a little note here. You are the best. Because you are. I want you to know that. But hey, thank you so much for spending your time with me, taking a look at this material. I really love talking about linear algebra, so I'm really glad you were able to hang out with me. And if you made it till the end, thank you so much. I want you to remember, no matter where you are and what you're doing, to always keep learning, keep dreaming, and follow your heart. And I will see you next time. Until then, make sure you take care.